Welcome to Cambridge IGCSE Physics, Lesson 49.1, Simple AC Generator. In this lesson, we will explore how alternating current generators work, examining their construction and operation. This is core content for your IGCSE Physics examination. Let's examine our learning objectives for today. By the end of this lesson, you'll be able to, first, describe the simple form of an AC generator, including its main components and structure. Second, understand how rotating coil or rotating magnet designs work to generate electricity. Third, know the use of slip rings and brushes in maintaining electrical contact. These objectives align with Assessment Objective 1, Scientific Knowledge, and Assessment Objective 2, Application of Concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, AC, generator, which means a device that converts mechanical energy into alternating current electrical energy. Second, alternator, which means another name for an AC generator commonly used in automotive applications. Third, slip rings, which means continuous metal rings that maintain electrical contact with rotating parts. Understanding these terms precisely is crucial for exam success. Let's explore the basic structure of an AC generator. The fundamental components work together to convert mechanical energy into electrical energy. Every AC generator contains these essential parts. First, the coil, which is a wire loop that rotates within the magnetic field. Second, magnets, which create a uniform magnetic field between north and south poles. Third, slip rings, which maintain electrical contact while the coil rotates. The operating principle is electromagnetic induction, discovered by Faraday. When the coil rotates, it cuts through magnetic field lines, generating electricity. The diagram shows how these components are arranged, with the coil positioned between the magnets and connected to slip rings for external circuit connection. Now we examine how the AC generator works. The operating principle is Faraday's law of electromagnetic induction. This states that changing magnetic flux through a coil generates an electromotive force. The process works as follows. First, rotation occurs when the coil turns in the magnetic field, either by mechanical force or motor. Second, induction happens as the rotating coil cuts through magnetic field lines, changing the magnetic flux. Third, output is produced as alternating current flows in the external circuit. The key equation for a straight conductor is EMF equals B times L times V, where B is magnetic field strength in Tesla, L is length in meters, and V is velocity in meters per second. The diagram shows the coil cutting through magnetic field lines as it rotates. Let's work through our first example. The problem states, a coil with 100 turns rotates in a magnetic field of 0.2 Tesla. Each turn has area 0.01 square meters. Calculate maximum EMF when rotating at 50 Hz. We are given N equals 100 turns, B equals 0.2 Tesla, A equals 0.01 square meters, F equals 50 Hz. We need to find the maximum EMF. Step 1. Write the equation. We use EMF equals N times B times A times omega, where omega is angular velocity. Step 2. Calculate omega. Omega equals 2 pi times F, so omega equals 2 pi times 50, which equals 314 radians per second. Step 3. Substitute values. EMF equals 100 times 0.2 Tesla times 0.01 square meters times 314 radians per second. Step 4. Calculate the answer. EMF equals 6.28 volts. Example 2 shows the AC generator output graph. The problem asks us to sketch EMF variation with time for a rotating coil. The key features are, first, a sinusoidal waveform is produced because the EMF varies as sine of the angle. Second, maximum EMF occurs when the coil is perpendicular to the magnetic field, cutting maximum field lines. Third, zero EMF occurs when the coil is parallel to the field, cutting no field lines. Fourth, one complete cycle occurs per rotation of the coil. The frequency equals the rotation rate in Hertz. The graph shows a typical AC output with peak EMF of 10 volts and frequency of 25 Hertz, giving a period of 0.04 seconds per cycle. Understanding the difference between slip rings and split ring commutators is crucial. The key difference is that the contact method determines the output type. For AC generators using slip rings, continuous rings maintain the same connections throughout rotation, so output alternates between positive and negative, creating true alternating current used for AC power generation. For DC generators using split rings, the split ring reverses connections every half turn, so output maintains the same polarity, creating pulsating direct current used for DC applications. In practical applications, power stations use AC generators because AC can be easily transformed to different voltages for efficient transmission over long distances. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, name 3 main parts of an AC generator. Think about the essential components we discussed. Question 2 is intermediate. It states, explain why EMF varies sinusoidally with time. This requires you to apply electromagnetic induction concepts. Question 3 is advanced. The question is, calculate EMF for a 50-turn coil with area 0.005 square meters in a 0.3 Tesla field at 60 Hz frequency. This tests your mathematical skills. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how AC generators apply in practice. In power stations, massive generators convert mechanical energy from steam turbines into electricity for entire cities, using the same electromagnetic induction principles we studied. In wind turbines, rotating blades turn generators to convert wind energy into clean electrical energy for the power grid. In car alternators, the engine drives a small AC generator to charge the battery and power electrical systems while driving. These applications show why physics matters. Career-wise, understanding generators opens paths to electrical engineering, renewable energy development, and power systems design. Looking to the future, clean energy generation becomes increasingly important for environmental sustainability. Let's review the solutions. For question 1, the answer is rotating coil, magnets, and slip rings with brushes. These are the 3 essential components of any AC generator. For question 2, EMF varies sinusoidally because it's proportional to the rate of flux change, which varies as sine of omega t as the coil rotates through the magnetic field. For question 3, using EMF equals N times B times A times omega, EMF equals 50 times 0.3 Tesla times 0.005 square meters times 2 pi times 60, giving 2.83 volts. Exam success tips. When describing structure, always mention coil, magnets, and slip rings. When explaining induction, link to Faraday's law and flux change. Show all calculation steps with units. Draw clear, labeled diagrams. Let's summarize today's lesson. The key points to remember are, first, structure. An AC generator consists of a coil that rotates between magnets, using slip rings to maintain electrical contact with the external circuit. Second, principle. Electromagnetic induction generates alternating EMF as the rotating coil cuts through magnetic field lines at varying rates. Third, output. The result is sinusoidal AC voltage suitable for power generation and transmission applications. For further study, review electromagnetic induction principles from previous lessons, practice generator calculations using the EMF formula, and compare the differences between AC and DC generators. Understanding AC generators is fundamental for appreciating modern electrical power systems.